start by the first lecture on principle of impulse and momentum and how to use that to formulate kinetics of particles. So, this is what we're going to do. We start from the Newton's second law again, that sum of the forces on a particle is equal to mass times rate of change of linear velocity, mdv over dt. And then we directly multiply both sides of this by a dt and integrate, right? So we have that sum of the forces is equal to mdv over dt. We cross multiply by dt and we integrate both sides. This is from t1 to t2. This is from v1 to v2. And then we call this quantity on the left hand side, which is the area under the force time curve. Okay, the integral of force versus time. We call this linear impulse, and there are so many symbols. In your textbook there is none, but I suggest we use I for impulse, as can be seen in other textbooks. And here, assuming that m is constant, or if you want, m can be inside dv, so it could be d of mv, and then integral of that is going to be mv1 minus mv2 minus mv1, right? And so if you remember this mv, we call it either p or l, linear momentum. So it is going to be p2 minus p1. So this principle says that the linear impulse applied to a particle is equal to its change of linear momentum, and this is what we call principle of impulse momentum, which you can see here. And the linear momentum is what we know from the past. The new quantity is this guy, integral of force versus time, which we call linear impulse. The unit for that is Newton's seconds. We had something very similar to this, which was integral of force versus displacement, integral of FdR, and we call that work. Right? So remember, the area under the curve of force displacement or position was work, and that was a scalar quantity. And the unit for that was Newton meter or joules. Here, this is the integral of force versus time. It is a vector quantity, so linear impulse is not a scalar, it is a vector. The unit for that is Newton second. Okay, so and then we use this formulation for solving kinetics of particles. And you might say, well, why should we derive again another formulation for kinetics of particles? We have second law of Newton, then we derive the work energy principle, and we learn that in cases that the time or acceleration is not needed, work energy principle deals with the scalars and typically provides a faster and simpler solution. And now you might say, what's the need for this third formulation? And I tell you, there are, again, problems in which this guy here, this new formulation, can solve much easier and much more convenient than second law of Newton. What type of problem? We're going to see typically the problems that either we know this integral of force versus time, but most of the time we don't know, and this left-hand side is zero or negligible. So the quantity on the right-hand side is zero. In other words, mv2 is equal to mv1 1, and so it means that the linear momentum is not changing. And we're going to see it in this lecture or next. We call it principle of conservation of linear momentum, and that conservation of linear momentum can be used in a bunch of problems. The most important one is impacts and collision problem. In those kind of problems, this method is the way to go. One other thing is the notion of average force. So in collisions, or the places that you have an impulsive force, okay, so you have a force that has a huge magnitude but a very short duration, right? That's typically what happens in collisions, in explosions or so on, right? In a very short time, a large force is applied, and typically the type of force is not like a simple function that we know, like a polynomial or sine or logarithm or power function or so on. It's kind of an impulse function. There could be some oscillations in it, even in that short duration. And typically measuring these is not super easy unless you have a very fast force transducer. So what they do, instead of defining this impact or collision or whatever impulsive force it is by a function, because it's typically not a normal function, what they do, they're not going to define a function for it, they just show it by the average of force, right? So what is the average force here? So what was the impulse defined? Linear impulse was area under the curve of force times t. So if I can find the area of this shape here, and then say, instead of this variable force, let's assume that the force in the whole period of t1 to t2 was a constant number, we call it f average. If that was the case, then this area, I say, if this area is equal to the area of that rectangle, right, which is f average times t2 minus t1, in other words, the impulse of the f average is the same as impulse of the actual f, then I call this the average of the actual f, right? So I say that the impulse from the actual force is integral of f d t, assuming that there is one single f, and the impulse of the average force is f average times what? t2 minus t1, and from here I find the f average. I say f average is the integral of f dt divided by delta t. Okay, and if I take magnitude, then it's the magnitude of impulse divided by magnitude of the time period. Now, what does it mean physically? It's just a number to represent this whole fast varying function that might not be a regular function. Does it mean, for example, if we say this is 100 Newton, right? Does it mean that the impact force is 100 Newton? No, of course not. So there are some times during the short period of maybe so many milliseconds that this is way above 100, and sometimes that is below. It's like when we say in this society, we say the average household family income is like $55,000 in the US. What does it mean? Does it mean that all families have the same? No, it's just an average statistics to represent the whole data, right? So there are a lot more and a lot less, and that's the same thing here. Okay, so it's just a way to represent this fast varying function. So just keep that in mind, the average force. Now, actually, let's take a look at one problem that involves this average force, example 63, and then we'll try to solve another problem. And we solve a particles kinetic problem, this time using the principle of impulse momentum. let's see what we can do. So this problem is basically you have a golf ball and you have a camera that can capture every 1 millisecond. So it can capture 1,000 frames per second. It's a very fast camera. And then you have a ball which is 1.62 ounces and 1.68 inches in diameter. You hit it with a club. So initially the ball is stationary. When you hit it, it starts flying in the air, and then your camera keeps taking frames. And if you look at that, you see a picture like this, where the ball is traveling at angle 21 degrees with respect to the x-axis, and the distance traveled between each two frames by the ball is 1.9 inches. Now, if you assume that the contact between the club and the ball, in other words, the impact period was only 0.6 milliseconds, what was the average force that the club applied on the golf ball? Right? And here we have to do it as a vector. So this is what we do. We basically directly use this guy. F average is integral of force versus time over T2 minus T1. But remember that we do not have here a curve of force versus time. That curve does not exist here. So we cannot calculate the area under the curve. But from this top principle, we know that this area under the curve, this guy, is equal to what? mv2 minus mv1. So instead of that, if I can calculate what? mv2 minus mv1 divided by t2 minus t1, that I can calculate. By the way, here, this quantity is actually what? You see, this is delta P, right? This is change in linear momentum, and this quantity is what? Delta T. So delta P over delta T is what? F average, but dP over dt is what? Look here. What is dP over dt, right? This here, if I take m inside, this is dP over dt, right? So you see here that if I take this away for a moment, what is dP over dt? dP over dt is F instantaneous, but delta P over delta T is what? F average. It's like when we did instantaneous velocity and average velocity. Instantaneous velocity was dr over dt, average velocity was delta r over delta t. The same thing here, dp over dt and delta p over delta t. So that might be a good thing to basically add to your lecture if you want. Okay, now going back. So what we need here is mv1 and mv2, where v1 is the velocity of the golf ball before the impact, and v2 is the velocity after the impact. Well, velocity before impact is 0 because we hit it when it was stationary, so that is gone. So it's gonna be m, which is 1.62 ounces, and you know how to convert ounces into pounds, right? You just divide it by 16. So it is 1.62 divided by 16. So that is in pound mass now. And then we have to calculate velocity v2, and then delta t was 0.0006 seconds. Okay. And if you want to stick to the standard units, then we have to also convert this into feet per second, right? The velocity. So now how do I calculate that? So this object is moving on a line. So I know the unit vector for the velocity. It is a unit vector with angle 21 degrees with respect to the x and y axis. So I can find that. And then the magnitude of this velocity, since it's uniform, it's considered uniform velocity here. No mention of it changing. It is equal to the distance traveled divided by the time frame between the two snapshots. And the distance traveled is 1.9 inches, which is captured every 1 millisecond, right? So what I need here is I multiply the magnitude of the velocity, which is 1.9 inches. First we divide it by 12 to convert it to feet, and then this distance traveled is captured every 0.001 seconds. So this is the magnitude of your velocity, and then this should be multiplied by what? By the unit vector of a line with 21 degrees, which we know it is what? Cosine of 21 degrees I plus sine of 21 degrees J, right? So if this is your x and y axis, your velocity is on this line. And this is the unit vector u of v, where this angle is 21 degrees. So now if we simplify this and calculate it, you're going to get 775 I plus 297 J, and the units is going to be pound force. Okay, so this is how you solve example number 16.3. And if somebody says what is the magnitude of the average force, then you just use what? The square root formula, right? So how much was the magnitude of the average force? You just use the square root formula in this case, which is 829 since they all rounded it to correct decimals, I rounded to no decimals. Actually, in this example the textbook did not provide decimals, so I round this also to the nearest full integer number, which is 830. So this is almost that much. So the golfer could apply 830 pound force with the club on average on the golf ball. It doesn't mean the actual force versus time was this constant number, but this is an indicator of how hard the guy hit the ball, right? So if you hit it harder, probably which number do you think would change? If you can hit it harder and the direction of the golf ball does not change, so it goes on the same direction, 21 degrees, which quantity would change, do you think? You're right, this guy here. If you capture it in the same time frame, it should travel a little bit more, which means it's traveling faster due to a harder impact, right? So that 1.9 could be 2 inches or so. Okay, so we looked at this example. Let's look at one more example. And then during the class time, depending on the time, we go over more problems and make sure that you got this topic very well. This is another interesting problem, 1614, where you have a 10 kilogram box starting from rest with a force that is not constant. This force is a trapezoid force, so you start applying until you get 50 Newton. Then for 4 seconds you don't change the magnitude, and for another 4 seconds you drop it down back to 0. In this case we assume that mu k and mu s are both equal to 0.2, which is a rare case. We typically have mu k less than mu s. In this example, textbook says consider them to be equal. Then tell me after 12 seconds how fast the box is moving. Okay, so this is what I would like to do. So what I would like to do is I would paste the object here, then also the force versus time here. And then write down what we have and what we don't. So velocity 1 in magnitude is 0. The mass of the box is 10 kilogram. Mu s is the same as mu k, and it is 0.2. And we want to know after, I guess it was 12 seconds, right? After 12 seconds, what is the velocity? So knowns and unknowns, then we have to draw the free body diagram. Do we have to do it here? Yes, anytime you do kinetics problems for rigid body or for particle, you always draw free body diagram. So that's the same thing here. So we draw our FBD. We have the force, of course. We have the gravity. We have a normal force, and then we have friction backwards, F. Now here I'm not going to call it Fk or Fs. We're going to decide on that. Why? We have to see first if that force is capable of moving it or not, and mu s is given. Then we go forward from there. Clearly in here, a simple xy coordinate traditional is sufficient. So we have our coordinate system in. Now it is time to apply the equations. But before I move forward, let me ask you this important question. Why shouldn't we use the second law of Newton directly? Can I do that? Sure, why not? But the thing is, when we say F equal m dv over dt, right, or F equal m times a, m is constant, but the acceleration of this particle is not constant, right? Acceleration of this particle is time dependent. Why? Because f is time dependent. So a is f over m. Since f is a function of time, then a acceleration will be a function of time, which is okay. And then if you want to calculate the change in velocity, you have to integrate acceleration a of t versus time, which is, again, that's kind of what we are doing here. Okay, so it's not the case that acceleration is constant. It's not. Acceleration is time variable, or time varying, actually. Now, how do I know that I cannot use work energy in this case? Why can't I use work energy? That's typically the fast solution. Why? Yes, you're right. Because somebody says what? Time. At t equal 12 seconds, what is v2? They didn't say after it moved 5 meters, what is the velocity. Time is involved, so work energy is not the way to go. Okay, so we have to use the principle of impulse momentum, or directly the second law of Newton. They are equivalent, basically. They are not going to give us much of difference in this case. So just to practice, we're going to use the new law, which says I, the integral of f dt, is equal to what? mv2 minus v1, right? So that is my principle. Integral of summation f dt is equal to mv2 minus mv1. So we're going to use this rule, but this is a vector equation, just like f equal ma, that we wrote it in the x direction. It became sum fx equal max, in the y sum fy equal may. This is a vector equation, so I can write this one time along X direction, y and time, I can write it along y direction. If I write it along x, it is going to be sum fx integral dt is equal to mv2x minus mv1x. And then the same thing in the y direction. So remember, any vector equation can always be written along any axis that you want. Good. Now what? So we're going to use both of them in this case. Let's first focus on y. In the y direction, what is summation of the force? It is n minus mg. And we know in the y direction, the object never has any velocity, not before or not after anything, before or after you apply f. So both of these velocities are equal to what? 0. The object in here is not supposed to move off the flat surface. So this total integration versus time should be 0, which means the force itself, sum Fy, should be 0, right? So if that's the case, it means summation Fy, which in this case n minus mg, this guy should be 0, so that integral of that versus time is 0, and therefore n is equal to mg, which is 10 times 9.81, so 98.1 Newton. And you see, basically, this is the same as sum Fy equals 0. So here, if I apply second law of Newton, or the second, which is because this is the second law of Newton just written in a new formulation. They both give us the same thing. Now, if I go in the x direction, some forces in the x direction is equal to what? Integral of f of t, right? This force, minus friction. This is sum of the forces. If I integrate this versus time, this is equal to mv2, that I don't know, minus mv1, which is 0, right? Because I start from rest, and m is 10, and times v2 of x, which is the unknown of the problem. Good, so it seems like I can use this. Now, I can separate this integral, right, because it's a subtraction, so I can say this is integral of f dt minus integral of friction dt, right? I can separate it. Integral is a linear operator, I can separate. So this is quite clear, right? That's the area under the curve, that's the area of this trapezoid. This is what? This is the integral of friction, and typically we know friction is a constant number, it doesn't change versus time, so I can bring it out, and so this is going to be f delta t. The only problem is, what is f? What formula should I use for f? Is it fk? How do I know? Especially in the beginning, right? In the beginning, you're not applying any force, right? Your force is 0. Does the object start to move right away? No. Because there is friction and there is no force to move it forward. So of course it's not going to move forward. Now when you make that f, you see it's linearly changing from 0 to 50. When you make that f, let's say 10 Newton, okay, here, at some time here, that force is 10 Newton, which is, or let's say 12.5 Newton at 1 second, because the slope of this is 50 over 4, which is 12.5. So at 1 second, the force is 12.5 Newton. Is that enough to start the motion? How do I know? Well, I have to compare it against what? The max friction, because we know the mechanism of friction. The friction will keep up growing and opposing the applied force until what? A max capacity, which is mu s times n, and then after that, what happens? The friction cannot keep up with you anymore. It surrenders, it gives up, and you push the object now. The motion starts, And when it gives up, the magnitude of it drops all of a sudden to a little bit smaller number, which is mu k times n, right? So in this case, if I show you, and you know that from physics, just want to remind you, if this is the applied force and this is the friction, if I can apply it and show you a graph, so when you apply this force, friction keeps growing, but friction never surpasses, never exceeds the force that you apply. So if you apply 2 Newton, it gives you what? 2 Newton. Surface only generates 2 Newton friction to cancel your force and stops the motion. If you go 5 Newton, it goes 5 Newton. If you go 10, it goes 10. So it keeps up with you on a slope of 1 to 1, right? So on this line, the slope is 1, or the angle is 45 degrees. So here, basically, F equals F. So it keeps up with you until and cancels. Again, friction never goes above your number, right? You never seen in real life that friction pushes you back. So you try to move a fridge on the floor forward, but friction overcomes your force and you're being pushed backward. It's not going to happen. It's a reactive force. F is a reactive force. It's never going to pass you, okay? F is always less than or equal F. It's never going to exceed. But it cannot keep up forever. At some point, it gives up. What is that point? That's where friction is equal to what? Mu s times n. This is the maximum static friction that you can have, Fs max. And when it drops, when the motion starts, then it drops now to another level, which is smaller than the max. And this new level, now that the motion started, this number is what? Mu k times n. And that's because typically mu k is less than mu n, mus. Now, in this case, the textbook said they are equal, which is not super realistic, but fine if that's the textbook wants us to think. Not that I accept it, but we just want to solve a problem. So here is when the motion has not started, so this is the static region, and this is what? The kinetic or dynamic region. Here the motion exists, here it does not, right? So you see, the surface can keep up with me until some number. And what is that number in this case? That number is mu s, which is 0.2 times n. And n is 98.1. So in this case, if I look, Fs max is going to be mu s times n. So if I multiply that number by 0.2 until 1962 Newton, the surface can withstand and stops the motion. Now, in this graph, at what time point do I pass that 19.62? Well, I have to find that time point, right? Because this increases from 0 to 50. So what I do here is, first I find the equation of this line. In here, f versus time for this first portion, it is equal to, since it's passing through origin, it's just a simple slope times t. What is the slope? It is 50 over 4, clearly, right? Now I want this number to be equal to what? 19.62, and from here I can find the time at which the motion starts. So I multiply that by 4, divide by 50, right? Which is going to be 1.57 roughly. So the motion does not start immediately. We have to wait until 1.5 seconds. 7 seconds to start the motion. Therefore, when we integrate here versus time, you see here, I'm integrating from time t1 to what? t2. What is t1 and what is t2? I cannot simply come and say, well, t1 is 0, t2 is 12. No. t2 is 12, right? Because that's what we want. But t1 is when the motion starts, and that is 1.57. Okay, that way I can do it. So if I continue here, this is going to be the integral from 1.57 to 12 of ft minus, now in that region, I know the motion exists, so this guy is going to be now what? Fk, and Fk is what? Mu k times n of integral dt, and again t is from 1.57 to 12, so this is a constant. I brought it out of the integral. This is equal to m times v2x, right? So this is integral of dt, so it's going to be delta t. Mu k I know, and I know everything I know. The only thing I need to calculate is this guy. What is that? And that is the area under this curve, but not directly calculated from origin. It is actually from this point onward. So if this is 1.57, I want this area, which is 2 trapezoid and what? A rectangle. So if I want to calculate the impulse in that region, so what is the impulse? Integral of f versus t between 1.57 and 12. It is the first trapezoid. It's between this number and 4. The height is 50. So it is going to be 50 divided by 2 times, or actually no, and this number, remember, this number we also need, this one was 19.62. So it is this number, 19.62. I need to clean this one up. So it is going to be 50 plus 19.62, sum of the two bases, times the height, which is 4 minus 1.57, the whole thing divided by 2, right? So this is the first area. The rectangle is very easy, it's just 50 times 4. And the last rectangle also, the last triangle is also quite easy. It's 50 times 4 divided by 2. So this guy is 200. This one is 100. That's 300. All I need to calculate is this number, right? So 6962 times 4 minus 1.57 divided by 2, and then the whole thing plus 300, right? Which is 384.59. So 384.59 Newton seconds. This is this guy that I need here. And I write it down, 384.59. This mu k times n, we know that was 0.2 times 98, which is 19.62 actually. This is simply 12 minus 1.57, which is 10.43. And all I need to do is now calculate V2 of x. right? So that's number minus, so 384.59 minus 19.62 times 10.43, the whole thing divided by 10, which is 1799. If you want to round it, you're going to get 18 almost. So you end up with 18 meters per second. Okay, so we have to make sure that the motion exists before we can just simply apply anything and solve the problem. That's the major thing here. Okay, so I guess I could cover the base, the first topic, and use it to solve problems. Now, if you remember, these are, because this one I could easily also solve with second law of Newton, so it's not a big deal. What really matters and the real application of this method is when an impact is happening. And that's where the next topic comes into play, conservation of linear momentums and impacts. So now that we have some time, I would like to continue this and move forward into the next topic and use our time here. So when is it that the linear momentum is conserved? Okay. So according to this principle, this quantity mv is conserved, which means it doesn't change, means mv2 is equal to mv1, or the left hand side is equal to 0, right? So when is it that the integral of force versus time is 0? When the f is 0. That's the only solution, because time keeps changing. So first of all, when we have more than one particle, now let's consider this for more than one particle. So if we have more than one particle, what happens? So here, assume that we have two particles, particle A and particle B. And in general, not only there are internal forces between these two particles, FAB and FBA. So here, these two are internal forces between the two particles. There could be some external forces applied to these particles from outside, right? And if we write this equation for each one of them and then add it together, what happens? So let me do it very fast here. And then we go back to the conservation principle. So here is one particle, here is another particle, and here, let's say this is all of the external forces that are applied to particle 1. The same thing here, let's say this is all of the external forces applied to particle 2. And again, this is M1, this is M2. And then there are internal forces between them. Clearly, these internal forces are so this is F of, this is the force applied to 1 from 2, this is the force applied from on 2 from 1. They are clearly action and reaction. The external forces are separate. And again, if I write the impulse formula for each one, you would get that the integral of all of the forces, because it's summation, right? So it's the integral of summation of forces dt is equal to integral of F1 external plus F12 dt is equal to m of v2 of object 1 minus m of v1 of object 1. And let's just not use 1 and 2. Actually, let's go with the textbook naming. Call them MA and MB because that makes life easier, because here we are using 1 and 2 for time points, not for objects. So I would call this f of AB, call this, and let me use the same notation as your textbook so that you don't see 10 different notations. Yeah, FAB. Okay, and this is FBA, and I would call this FAE external. This is, I would call FB external. So this is going to be FA. This is going to be FAB, and this is going to be for object A. Similarly, I write the same principle for the other object. And this is m of A, and this is m of B. There are too many superscripts and subscripts that we have to pay attention to, and arrows, to write it properly. Okay, so now what I do, I sum these two up. What do I get if I sum them up? When I sum them up, the left-hand side will be FA external, FB external, and then these two would cancel out, right? Because they are action and reaction, and I'm integrating versus time, so I can add them first and then integrate versus time, and addition is 0. And here I would add these two, call it the total linear momentum of system in position 2. This is total linear momentum in position 1, and this is total external forces. So it is going to be integral of all of the external forces dt is equal to total momentum right? Or if you want, I can simply put the 2 here. And then put a 1. There we go. Then next time I put a 1 here. So what does this mean? Means if you have a system of particles, and this should be negative. If you have a system of particles, when you write the principle of impulse and momentum, the total momentum of the system in position 2 minus the total momentum of the system in position 1 is equal to the impulse applied to the system only by what? External forces. So just like the second law of Newton, remember, for a system of particles, what did you have? If you remember, this is what you had. For a system of particles, only external forces could give acceleration to the center of mass, and this was the mass of the whole system, right? So internal forces play no role in creating acceleration for center of mass. Similarly, internal forces play no role in changing the total linear momentum. Only the external forces do, okay? Now, if these external forces do not exist or they are negligible, so they are very small or zero, like this case, only internal forces exist, what happens? Yes, you clearly know that the left-hand side is zero, therefore the right-hand side is zero, which means the total linear momentum of the system in position 2 is the same as that in position 1. In other words, the total linear momentum of the system is not going to change, and that's what you can see here. The total linear momentum is a constant, and that's what we call conservation of linear momentum for the entire system. And this is what we use as one part of formulating impact and collision problems. Why? I'll tell you in a second. But before we go to that, which is really important, is since this quantity, total linear momentum of the system, is constant, right? Since this guy is constant, what does it mean? Can I divide this constant number by the total mass of the system? Sure. What do I call it then? What is the total linear momentum of the system divided by the total mass? Yes, you are right. That is the velocity of the centroid, V of Cm, correct? If you remember, R of Cm, the position of the centroid, was, if you have two particles, it was Ra Va plus Ma, Rb Mb divided by Ma plus Mb. And if you take a time derivative from this, what would you get? You get velocity at the centroid is equal to Ma Va, because m's are constant, at least we assume here, Mb Vb divided by what? Ma plus Mb, right? So that's the velocity of the centroid. But now here the numerator is constant when external forces don't exist, and the denominator is constant. So this whole thing have to be what? Constant. So it says, if there is no external force, the velocity of the centroid does not change, stays constant. Absolutely. Could we predict that from second law of Newton? Yes. Look at the second law of Newton. If the external forces are zero, what does it mean? It means this acceleration term is equal to zero. And when acceleration of the centroid is zero, what does it mean about its velocity? Sure, it has to be constant, otherwise the acceleration is not zero. So in the absence of external forces, the velocity of the centroid is constant, or we can say the total linear momentum of the system is constant. And again, we call it conservation of linear momentum, which is very important in impact problems. Why? We're going to see in a second. So hopefully so far so good. Now, let's see. Impact, collision, these are the stuff that happens a lot in real life, whether you're playing pool or billiard, whether you are, God forbid, in a crash, or whether you are creating or forming the metal, or basically putting some deboss or emboss or something on the metal, right? Like this. They happen a lot. There are very basic things that they happen on a daily basis, a lot of them, whether you don't pay attention and run into somebody or into the wall, they're all collisions or impacts. Now, the main thing about impacts is this impulsive forces. This is the nature of impact. A very, very short period of time, typically, and a huge exchange of force. Okay, that's what happens. So here we have these two particles, and they hit each other. And when they hit each other, what happens? They exchange these internal forces, right? So this FAB or BA is the impact force that these two particles apply together. Now, during that impact period, is there no other external force? Well, typically, yes, there is. At least we can see the gravity is always there regardless. So can we neglect it and then say because there is no external force on this system of particle, then the total momentum of the system is conserved? Can I say that? Because that's exactly what we do when we solve impact problems. So we neglect the gravity. Well, should we neglect it? We know they exist, but why do we neglect them? Why? Sometimes these masses are not really small and the gravity forces are not small. Should we neglect them? Well, it depends on the application, but mostly we can because what? Two things. First of all, in most of the impacts, the magnitude of the impact force is significantly bigger than gravity. Okay? It is typically significantly bigger. But you might say, well, when two cars hit each other, their masses and the gravity is huge. And although the force of impact could be bigger than several tons of force, but it's not going to be billions of newtons, right? It could be probably 10 times bigger or so, maybe. I'm not exactly sure, but we can find out. So still, it's like maybe gravity is 10% of the impact force because these two objects are huge masses. Should we neglect? The problem is then not only the magnitude comparison, it's the time period. In the small time period, because typically this difference between T1 and T2 in impacts are milliseconds. You don't have an impact that takes place in 10 seconds and continues for 10 seconds. It's a very, very fast thing. And so the effect of a constant force of gravity in that short period is the force of gravity itself times the time difference. And since the time difference is very small, when it multiplied even by a big force, still will create a very small impulse. So, should we neglect the external forces? I would say it depends on the application, but for most of daily life routine applications, typically we can neglect and use what? The principle of impulse and momentum and the conservation of total linear impulse of the system. If the masses are huge though, and the application is super accurate, we cannot really let go of anything, then we cannot use this. So it depends on the application, but again, for many of routine applications we use on a daily basis, yes, we are going to use the fact that even if there is an external force, which typically is only gravity at that short time period that still exists, we neglect them. And so if we do, then now we have our first formula for solving an impact problem. Conservation of linear momentum. So what we do in this part of the textbook, and from this point on, we use the prime notation. Prime here does not mean derivative or anything. Prime here means velocities after impact, and without primes means velocities before impact. In other words, instead of using 1 and 2, 1 for before and 2 for after, your textbook is using no prime for 1 and then with prime for 2. Okay, so prime means after. Now the question is this. I have two particles. They are coming at each other and hit. Before they hit each other, I know their velocities. So in other words, if I go back to this notation, I know V of A and V of B, right? Two objects are colliding. Before impact, I know their velocities, VA and VB. And I'm interested in what? Finding their velocities after impact, V prime A and V prime B. Can I find them? Even if I consider the impact to be happening along a simple line, which we call direct central impact. So the simplest type of impact that can happen is when two objects hit head-on. Okay, or like one object is tailgating the others faster and hit it. So there are two types of impact that we study in this course: direct central and then oblique impact. Okay, oblique central. What's the difference between these two? The difference is this. So in direct central, the relative velocity between the two particles is collinear with the line that connects the centers together. Okay, so here, this is the line along which the impact is happening. This is particle 1 and this is particle 2. And let's say they are moving head-on directly toward each other. So this is VA and this is VB, and then this is also the line that connects the centers together, the red one. So V of A with respect to B, we know V of A with respect to B is VA minus VB, right? Relative velocity, what we learned at the end of chapter 13. So here, what is VA minus VB? So what we do when we subtract two vectors, how do we subtract two vectors? Remember? So if this is VA in general and this is vector A and this is vector B, if we draw both of them from the same point, then A minus B is what? Connecting the end of negative, which is B, to the end of positive, which is A. So this is A minus B, right? That's how we do it. So here, if I draw both of them from the same point, so that is A, this is B. If I bring V of B here, then connecting the end of B to end of A, like this. This is V of A with respect to B, and this is VB if broad, and the origin of it is the same as origin of VA. So clearly you see the line of action of VBA is the same as what? The line of action of the line that connects the two centers together. So since these two, this black one and the red one, are parallel, we call them direct central impact. While in the oblique impact, what happens is you have one object here and you have another object here. They come at each other, but not directly. So they come here and then they hit here. And let's say they hit here. So this is the velocity VA in this case. And this is the velocity VB. They should not necessarily be equal. And then this is the center of A, this is the center of B. So here is the line connecting the centers. And if I draw VA minus VB, so bring VB here, basically, and connect the end of negative to positive, this guy here in green is VA minus VB, or V of A with respect to B. And clearly the green line and the red line are not collinear, so this one is oblique impact, this is the central impact. Direct central. Now direct central is simpler than oblique because in direct central your velocities only have one component. If you consider this line to be x-axis, then you're only looking at finding one component, x only. But here these have 2 or 3 components. So not only you have to find x components after impact, you have to also find y and z components. And we're going to see all of them. But let's say we are focusing on the simple case, direct central. So here, what I want is, if I know V of A and V of B before impact, so I know both of these guys, and I'm interested in finding V prime A and V prime B. What happens when they hit each other? How do they separate? What are their velocities after impact? Can I find it? Well, there are 2 unknowns, so I need 2 equations. But the equation I found, this conservation of linear momentum for the total system, just gives me 1 equation. Assume that this is a scalar equation in the x direction. So here you have 1 equation with 2 unknowns. So that's not enough. I need to bring in 1 extra equation. Where does that come from? That's come from something called coefficient of restitution. Something that you have seen in the course project, right? If you remember, in your course project, that is a projectile subjected to air drag and lift, and you continue simulating it. Every time that it hits the ground, it bounces back until it doesn't bounce back. If you remember, to model when it hits the ground, which is an impact, in the project, you are given a number, which is here. It says the coefficient of restitution is 0.6. What does that mean? So let's talk about this guy. So this coefficient of restitution, E, is a function of the nature of impact. What type of impact do you have? Is the impact something like these balls here, that when they hit each other, after impact, you don't see a significant amount of deformation, right? They hit each other and then separate very well. And if you look at the surfaces of the balls due to impact, you don't see much of deformation unless you use microscope or something. You can barely see anything because the objects are too rigid and they don't deform easily. Or it's something like this case, or this one. One or both of the objects are significantly deformed. So what's the difference between these two? Naturally, if we just want to think intuitively without getting too much into formulas. What's going on here? So here, before impact, you have VA and VB. So you have what? Kinetic energy, right? We know velocity means kinetic energy. So before impact, you have some kinetic energy in the system. When the impact happens, that energy is not going to be used to deform the surfaces of these objects. So it's not going to be converted into deformation, and what we call, if you have seen in your solid mechanics, we call it strain energy. It's not going to be converted into that. And so after the impact, we're going to get that energy back. It's like one object hitting a spring, right? The spring might deform a little bit, but once it comes back, it gives all the energy back. So here, during impact, maybe, not maybe, for sure, the surface of the objects would deform, but that deformation is small because the objects are too rigid for the velocity of the impact. They are quite rigid. And because the deformations are small, we can say they are what? Linear, or we can say they are elastic. That's what you learn, or you will learn in your solid mechanics course. When deformations are small and they are linear or elastic, the system behaves like a spring. So they deform a little bit, but they come back to the original shape and give back the energy. So when the surfaces give back the energy, what happens? The objects get their energy back, and so the velocities of after impact, or not call them velocity, the energy, the kinetic energy after impact is going to be very similar to the kinetic energy before impact, because it is not used to deform the shapes of the particles. On the other hand here, when two objects collide and they have some kinetic energy, one or both of them, and then a significant portion of that energy is used to completely deform the shape of the objects. Why? Because the objects are not super rigid in this case, and the velocity of impact is high. So the deformations are not small, the deformations are large. What we call in solid mechanics, we call them, instead of elastic, we call them plastic deformations. So deformations are plastic, they are permanent. Once the impact is over, the object is not going to get back its shape, it's deformed forever. And a lot of that kinetic energy is used to deform this shape. So this car is not going to bounce back with the same velocity that it hit this panel. If it bounces back ever, it's going to be with a very small velocity. That kind of impact we call plastic impact. So elastic versus plastic. And if it's perfectly plastic, means what? Means this guy is not going to jump back at all. And so the two objects would stick together. It's like when you have a pendulum, or one of the examples that you will solve in one of your homework is a pendulum, basically, that is used to measure the velocity of a bullet. So what you have is a pendulum here that is hung by a couple of ropes to a support surface. And then there is this bullet that is coming in. Again, I have to only use the bullets, not the cartridge. And then when it hits this, it's going to penetrate this object. And then basically it's not going to bounce back. They're going to become one object. So this bullet gives all of this kinetic energy to the system. So now they both have kinetic energy, and the thing will make this pendulum what? Go up a little bit. So you're going to get something like this. And then based on this change in the elevation of the box, you can find out how fast this guy was moving. So this is a perfectly plastic impact. They stick together. Okay, so now to formulate this nature of the impact, elastic versus plastic, we introduce this new quantity called coefficient of restitution, E. Now, how do we use that? How do we formulate it? Another way to express E mathematically is using the internal forces that are exchanged between the two particles at the collision. So here, these two particles are colliding. During the impact, they exchange this force called R. and then they get separated. So if c here is the velocity of each particle right at the impact, okay, so here we have a few time points, t1, t2, and tc. So before impact is t1 to tc, and after impact is tc to t2. So tc is exactly the time that the impact happens. T1 is a little before that, and T2 is a little after that. So here we are looking at two time ranges, T1 to TC and TC to T2, a little before and a little after impact. And R to be the impact force exchanged. So here we are writing the impulse momentum equation for particle A in the two time ranges. And we also write the impulse momentum equation for particle B in the two time ranges. And then, since the R's are equal, what we would do, we define the coefficient of restitution to be the impulse of the impact force after impact to the impulse of the force before impact. And from these two top equations, we can show that that is also equal to relative velocity of the particles after impact over relative velocity of the particles before impact with a negative sign. So the meaning of coefficient of restitution is it's the ratio of two impulses. But if you simplify, the one that we use and the one that is useful to us, the formal definition that we use for coefficient of restitution is this: negative of relative means subtraction, difference of velocities before impact over the same difference after impact over the same difference before impact, E. So now, for the central impact problem, where you have this object and then this one, and they come at each other with VA and VB, and with MA and MB, and then after impact they get separated with V prime A and V prime B. Now we're gonna have two equations. One, MAVA plus MBVB. And you see I'm using scalars because I assume that everything is happening along this line, so I decompose every velocity along this line. And I'm just looking at those components here. So that's one equation, and then I have E, which in our problems it is given to us. So if you cross multiply, you would get V prime B minus V prime A is negative E times VB minus VA. And so I can use this equation 1 and I can use equation 2 because again E is given to us. And V, A, and B are given, and I need to find the primes. So I have two equations, 1 and 2, and from these two equations I can solve for both unknowns. Sometimes maybe the problem gives you one of the after impact velocities and asking for before impact velocities. Okay, so this E is given to us in our problems. Now, what range of values do we expect for this E? This E, we can show that it is always in the range of 0 to 1. If it's 1, means that the impulse ratio is 1, And so you are not losing any energy due to impact. In other words, the impact is what? Perfectly elastic. On the other hand, if E is 0, means what? Means the relative velocity after impact is 0. In other words, V prime A is the same as V prime B, so the objects stick together. And it's called perfectly plastic. So perfectly plastic means they stick together, E is 0. Perfectly elastic means E is 1, and there is no deformation. Most of the time in real life, it's none of those. Unless, again, it is a special problem like this pendulum that I mentioned. Most of the time, it's somewhere between 0 and 1, like your project says 0.6. Typically, the harder the objects are, and the smaller the velocities of impacts before impacts are, the closer E is to the 1. The softer the objects are, or more deformable, and the harder they hit each other, E is closer to 0. Now, you see I mentioned that not only E depends on the material, whether they are rigid or they are flexible, it also actually depends on how hard the two objects hit each other. It does depend on VA minus VB. It does depend on the relative velocity before impact. But your textbook, for sake of simplicity, assumes that no, E is just a constant number for two types of material, but in real life that's not the case. In other words, in your example of the project, when you have this projectile, it comes and hits the ground here, right? Let's say the first time it hits the ground, it hits with a velocity of magnitude v equal 20 meters per second. You have some E here, and here the material of the ball and the material of the floor is the same. It's not going to change. So do I use a constant E for this impact versus the next one? Well, we know the next one is not going to happen with the same V, right? Because I lost a little bit of V here because of impact. There is some deformation, permanent deformation. And then the drag reduced the velocity. So the next one might happen with 16 meters per second. And then the next one might happen with 12 meters or 11 meters per second and so on. So do I use the same E in all of these cases? For your project, yes, you do. Use 0.6 for all of them. But in real life, please pay attention that that's not the case. Here you are hitting harder, so probably the first one is going to be maybe 5, then this one maybe 0.6, then this one maybe 0.7. Right? The easier the impact is, the smaller the velocities are, you're not going to deform as much, and E is going to go closer to 1. So ideally, E would increase as well. Maybe not this dramatically, but it does. Now, we need to know exactly E as a function of what? VA minus VB. We have to know that. But since measuring this is not an easy thing to do, and it is a little beyond the scope of this course, we're going to neglect it, and we just, in this course, assume that for our applications, we use a constant E. Okay, especially in most of our problems, the impact is happening once and not several times. Good. So now I know how I should formulate this. And I mentioned that here for you, how we solve this problem. Now, one last thing. Sometimes in the impact problems, it is asked from you, what is the change in kinetic energy? If somebody says, what is the change in kinetic energy due to impact, what is it? The change in kinetic energy due to impact is energy, kinetic energy after impact minus kinetic energy before impact. And kinetic energy after impact is what? Sum of the individual kinetic energies. So it's 1/2 ma v prime a squared. Sorry. Plus 1/2 mb v prime b squared minus the same thing before impact. So VA squared and VB squared. This is the change in kinetic energy. Now, if the impact is perfectly elastic, I encourage you to show that this guy is going to be 0 joules. It's not going to change. If E is 0, then this is going to be its max value. How much is max? Well, it depends on the initial value and the final values of the primes. But if there is a max, this max would happen at E equal 0. Okay? Because you're not going to lose typically all of the kinetic energy. Right? You're not going to have the case that both of these are 0 unless it's a really super hard impact. Even in this hard collision of the car with another car or something, after the impact, either they separate a little bit, or even if they stick together, they move a little bit. So they're not going to completely basically dissipate their kinetic energy. So it's never going to be equal to the initial kinetic energy. This guy is never 0, but you can see that this difference is max. Okay, so that is the other problem. Okay, I guess we have formulated this problem.